So probability that a point in the set P minus ball of Q comma R. So this is the this is the case when P and Q are like very far from each other, or sorry, probability that a point in this the ball outside radius 1 plus epsilon times r collides with a given point Q is at most 1 minus, as we calculate, 1 minus beta par k whole power tau. We can expand this to be 1 minus beta to the power k times 1 plus 1 minus beta to the power k plus 1 minus beta to the power k whole square plus and so on. So there will be like k terms in total, or sorry, tau terms in total. So this will be equal to or less than or equal to, because like we can upper bound each of these to be less than or equal to 1. So this will be less than or equal to beta par k times tau, and we fix tau to be 4 by alpha par k, so this will be 4 times beta by alpha whole par k. Okay, so now this is the probability that 2 points which are like at a distance apart, like at a distance at least 1 plus epsilon times r apart, collide. So now we can, with this probability, we can compute the query time. So if you remember the process, it's first we compute for a query Q, we compute h of Q, and then we go through the list and then go through the bucket B, which contains all points P such that h of Q equal to h of P. Okay, and as noted earlier, if we find a P such that distance of let's write this. If we find P such that distance of P comma Q is at most 1 plus epsilon times r, then we return. We don't even need to go through the remaining list. The problem comes when if all points are like, let's say if the number of points P such that is huge, but we want to upper bound this number. We already calculated the probability that such P and Q collide. So the expected number of P such that distance of P comma Q is greater than 1 plus epsilon times r, and h of P is equal to h of Q is given by so here we have this. That's the probability that they collide. So this is given by 4n times beta by alpha whole power k. Okay, yeah. So in the worst case, I mean, in the expected case, the list length will at least be this. So that's the expected amount of time to go through the list. Okay, and and to compute h of q itself, we need tau k time, because the matrix itself is of dimensions tau times k. Okay, so the query time will be or like will approximately be like discounting these constants tau k plus n times beta by alpha whole power k, and of course there will be a factor of d, because we are in the we are assuming that we are in the d-dimensional space, like so each point has d coordinates, so this factor d is kind of inevitable. Okay, now we want to choose k, we already chose tau in terms of k, but we want to get further conditions by minimizing this quantity. So differentiating this is not going to be very easy. So in fact, so we will do an approximate minimization by take tau k is equal to n times beta by alpha whole power k, and we already know what alpha power k is. So alpha power k is 4 by tau, again like discounting that. Yeah, we can also actually like have 4 here. So if we take tau k equal to 4n times beta by alpha whole power k, so this will be equal to n beta power k times tau. Is that okay? Yeah, so that's okay. So this implies that we get a value for k equal to n times beta power k. Alright, so let's see what this turns out to be. So so if we choose k equal to ln, yeah, this is going to be my final answer, so I know this. So we want to say that this is going to work for us. So let's do some calculation here. So we know that 1 by beta whole power k. Why is there ln? So this should be log actually, like it doesn't make sense to write ln to the base something else. So this will be log n to the base 1 by beta. So 1 by beta whole power k is given by n. Yeah, so this actually, so choosing this may not actually completely solve this equation, but we'll see that just choosing this value will actually work for our case. So in this case, the query time would be some d times tau k plus 4n beta by alpha whole power k. So we see what this thing is. So this will be d times tau k plus 4. So k is chosen as log n to the base 1 by beta. So beta power k times n will be 1. So 4 and 1 we will upper bound like very trivially using k. Okay, and yeah, in general, like we assume this this n, which is the size of the point set p, to be like very large. So, and since beta is a constant, so this turns out to be always greater than 1. Okay, so this will, we can upper bound this as 4k by tau k plus 4k by alpha par k. And so 4 by alpha par k, we chose as tau, we chose as 4 by alpha par k, so this will be 2d tau k. So in order, so this will be of d tau k. Okay, and yeah, k we chose to be, sorry, k we chose to be ln n by ln 1 by beta. And let's see what the value of tau exactly is. Tau is equal to 4 by alpha par k, and k we choose as given ln n by ln 1 by beta. So this will be equal to 4 by alpha power ln n to the power 1 by ln beta, 1 by ln 1 by beta. So this will be, so this quantity alpha power ln n can be written as n power ln alpha. And now if we take that to the denominator, if we take this entire thing to the numerator, then this will be 4 times n power ln 1 by alpha to the power ln 1 by ln 1 by beta. So this will be equal to 4 times n power ln 1 by alpha by ln 1 by beta. And we said that alpha is equal to, so at least let's look at the hypercube case. We said that alpha is equal to 1 minus r by d, and beta is equal to 1 minus 1 plus epsilon times r by d. Okay, so this was capital R actually, but for APQ we work with the capital and small r as r and 1 plus epsilon times r. So if you yeah, so here it is. So alpha is given by this, beta is given by this for hypercube metric with the Hamming distance as the distance function, and r we choose as 1 plus epsilon times r because like while solving APQ, that's the gap that we want to differentiate. Okay, so this is going to be our tau. Yeah, query time is like we argued it to be 2d tau k. So 2 times d times tau is given by 4n ln 1 by alpha by 1 by beta times k is chosen to be ln n by ln 1 by beta. So now getting rid of all the constants, so this will turn out to be O of ln 1 by alpha by ln 1 by beta times ln n, okay, times d. So this is going to be our query time. So as of now, this this ln 1 by alpha by 1 by beta is in terms of r and d, so it's fine, but let's try to get rid of them also and get a neater expression. So for that we will need this proposition. This is a so this proposition is given as this: for x belongs to 0 and 1 and t greater than or equal to 1 such that 1 minus tx is greater than 0, we have ln 1 by 1 minus x by ln 1 by 1 minus tx is at most 1 by t. Let's try to prove this. So consider that this function g of x is equal to 1 minus dx minus 1 minus x whole power t. So let's compute g prime x. So that will be minus t minus t times 1 minus x. So minus x, so that will become plus. Okay, so this is something like 1, or this is exactly equal to t times 1 minus x whole power t minus 1 minus 1. So we said that t is greater than or equal to 1, so this exponent is positive and x is something less than, in between 0 and 1, so this entire thing is less than 1, and we are subtracting this, subtracting 1 from this something which is less than 1, so this will turn out to be less than or equal to 0. Alright, so that means that g is a decreasing function. Now if we compute g of 0, so that will be 1 minus 0 minus 1 minus 0 whole power t, which is 0. And since g is decreasing, it means that g of x is less than or equal to 0, 0 for all x belongs to 0, 1. Alright, so from that, what do we get? We get that 1 minus tx is less than or equal to 1 minus x whole power t. Taking ln on both sides, we get that 1 minus tx is less than or equal to t times ln 1 minus x. So both of these are in between 0 and 1, so they have negative values. Let's make them positive by multiplying with minus 1 on both sides. So this implies that ln 1 by 1 minus x by ln 1 by 1 minus tx is at most 1 by t. Okay, so we have this. Now we will use this to bound our query time or get a neater expression for our query time. So we'll substitute alpha to be 1 minus r power d here and beta to be 1 minus given by this quantity. So then query time is equal to O of n power ln 1 by 1 minus r by d by ln 1 by 1 minus 1 plus epsilon times r by d times ln n times d. So now we use this identity with x equal to r by d and t equal to 1 plus epsilon. So then this will turn out to be O of n times 1 by 1 plus epsilon times ln n times d. Okay, so this shows that the query time we have is sublinear in n. Okay, that's with the query time. And the pre-processing space, so remember that for each point in P, in capital P, we are storing a matrix of dimensions tau cross q, tau cross k. So, and each point is of each point has d dimensions. So each entry has there are n entries in total. The dimension d, again, it's inevitable. So, and each matrix has size tau times k, so this will be equal to n d tau k. But if you see, the query time is of the same order, except that n is not there. So basically, we, for the pre-processing space, we have to multiply query time with n. So this will be O of n times 1 plus 1 by 1 plus epsilon times ln n times d. Okay, so that's the result that we have. Yeah, if we choose epsilon to be something significantly big, let's say 1 or 2, then we get this query time to be very nice. It will be something like n power 1 by 3, whereas pre-processing space will be n power 4 by 3, which is very good, which is less than quadratic space. Okay, so that's the general result that we have. So the general theorem, so these starting from this proposition, we did this for hypercube case, but in general this is going to be our query time, and the pre-processing space is this multiplied by n. So let's write that general theorem. So the main theorem is this. So it is possible, and assuming the underlying metric space has an LSH family or R comma Kepler comma alpha comma beta LSH family, we get the following theorem. It is possible to pre-process a set of n points in R bar D such that pre-processing space is O of n power 1 plus ln 1 by alpha by ln 1 by beta times ln n times d, and query time is O of n power ln 1 by alpha by ln 1 by beta times d. Okay, and yeah, of course this is a randomized algorithm, and each query is successful with probability at least 3 by 4. And again, we can boost this probability by having multiple data structures. One question is whether that will increase this query time. Yeah, that will increase, but we can ensure that using appropriate parameters, we can ensure that this query time still remains sublinear. Sorry, one small correction. This theorem is for the APQ problem, not for the approximate nearest neighbor problem. It's for the approximate proximity query. But as we have seen earlier, approximate nearest neighbor itself can be solved using very few, logarithmic number of calls to approximate proximity query. Okay, so yeah, till now we have seen how to solve approximate proximity query, assuming that there is an LSH family for the underlying metric space under consideration. There is no general procedure to come up with an LSH family for a given general metric space. So depending on what metric space is, the way of coming up with an LSH family differs. So now we will see